I'm sharing my screen. Let me know once it is visible. Let me. Can anyone confirm whether I can able to see my screen? Whether I'm audible? Sadhana, can you just confirm whether I am audible?
Yes, sir. Also, we can see your screen.
Yeah. Okay. Good. Fine. Okay. Good. So I will just recap through the things what we have done. So for opening the new case, so we have to go with this plus symbol new, create a new document. So in that we can get the blank page like this, and we can there we can able to start building our single line diagram. So in the right side column, first column is the AC elements. In the second column, the top one is the instrumentation element, and the bottom one is the DC element. So we in ETAP we have multiple studies. So the pencil symbol is the edit one. So there only we can add or delete any elements like transformer, cables, etc. Modification in the single line diagram we can done through this edit case only. Then after that, the PQ will be load flow analysis, and then this will be short circuit, arc flash, motor starting analysis, harmonic analysis, transient stability, relay coordination, then star protection. So these are all the other studies which ETAP can able to use. So after that, once we open the project, so first we need to include some basic information. Some information we have to go include in project, in the project information. So in the information page, it is an optional. We have to enter the project title, location, contractor, who the engineer who is doing the studies. These are all the very basic one. It is optional. Then second one is the standard. So standard is an important. So what standard you are going for? Consider as a base standard. So we have two options, IEC and ANSI. So that's standard we need to select, and frequency. So what is the frequency of the particular country? So I am in India. Here the frequency is 50 hertz. Someone in Philippines or US, their frequency is 60 hertz. So we need to select that. So the first two thing is the mandatory, and the unit system is English and metric. Two option is there, English for ANSI and metric for IEC. Then date format and currency, it is optional. So these are all the basic information we have to do it before starting any project or start doing any single line diagram. Then after that, I'm just made the two bus element. In our last class we just seen the two bus system. So in the two bus system, we have seen the bus, transformer, static load, motor load, capacitor bank. So I will just rebuild that one. So first we have to enter the bus element. So in the bus element we have to enter the id and the voltage. So now we consider the voltage as 230 kV. Then in the low voltage side of the transformer, I'm considering 11 kV. So by defaultly, uh, it will updated in the transformer. So in the transformer, you have to update the ID, then standard. So here also option is there. You can select it. But once in the main page we selected the IEC standard, it will considered here. Then in the rating page in the transformer, we have to update the power rating voltage. The voltage after entering the bus voltage, it is directly taking the bus voltage here. Then power rating, just I'm entering as a 50 MVA. Then impedance page, we need to enter positive sequence and zero sequence impedance. So if you don't have the actual data, then use the typical X by R value what the ETAP is given the option. So with that, we can able to get some values from ETAP library. So here the jet variation is to accounting the variation in the transformer tap impedance. So here we are entering 12.5 percentage impedance with respect to nominal tap. So whenever the transformer operating at the different tap, let's say the minimum tap and maximum tap. So for that tap, what is the transformer impedance? That impedance we need to encounter it here. We need to account it here. The next one is the jet tolerance. Jet tolerance. In the last session, I told that for the load flow study, we will consider the positive tolerance, and short circuit study, we will consider the negative tolerance. So it is based on the manufacturer. So each transformer manufacturer will give the transformer with impedance, that is for example, this transformer is 12.5 percentage impedance. With this 12.5 percentage impedance, there is some tolerance, so the transformer manufacturer will specify. So those transformer mostly will comply any IEC or ANSI standard. In IEC, there is some requirement for the tolerance requirement. So all the transformer complying to that standard has to comply that impedance tolerance within that limit. So that tolerance we will consider. So the positive tolerance we have to consider for the load flow study, and negative tolerance we have to consider for the short circuit study. So in the last session itself, I told you that it is one of the interview question, and that why we have to consider the positive tolerance for the load flow study and negative tolerance for the short circuit study. The reason is that to calculate the worst case scenario. So whenever the impedance we are considering for this load flow study, so we are considering the positive tolerance. It means the transformer offering more impedance, so that in the normal load flow analysis, so the voltage drop across the transformer will get increased. So that will give the worst case result at the remote end transformer, remote end buses. So only we are considering the positive tolerance for the load flow study, in the negative tolerance for the short circuit study. So in short circuit study, we are calculating the fault current at the particular buses. So when we are considering the negative tolerance, that time transformer offer the lesser impedance. Let's say if the tolerance is 10 percentage, means out of the 12.5 percentage, 10 percentage will be the negative value. So that time it will be somewhere around 10 to 10.5 will be there. So that is the impedance offered by the transformer. So it can contribute more amount of fault current. So the calculated fault current at the particular bus is high. So that is we have considered as a worst case scenario. So in the transformer tap, we have two options. One is the fixed tap for the off circuit tap changer, and LTC for the on circuit tap changer, and grounding. So grounding here we have to select the winding configuration. In the primary presently it is delta configuration, in the secondary it is the star configuration. So that configuration we have to select for the any load flow study. Then after that we have the static load here. So static load, as usual we have to enter the ID. Then after that we have to enter the power rating. So MVA, I am considering just a 5 MVA at unity per factor. So it means it will drop 5 megawatt of real power from the source. Okay. So just I am doing the simple load flow. So for executing the load flow, we have to go to the PQ, that is the load flow. In the right side, PV is the load flow for the single run. If we need to do the multiple run, means we have to turn on the auto run on or off. Once we run enable auto run, if we modify any values in the single line diagram, then the load flow will run automatically, so it will save some amount of time. So we can enable that. So after that we have the bus voltage. Now the load flow has been executed, so bus voltages is here. So in the high voltage side it is 100 percentage, in the low voltage side it is 99.96 percentage. So the load is trying almost to 62.3 ampere from the source. So up to this we have seen already. So if we need to change the option, so here we have the Y symbol is the display option. In the display option, what are the parameters we want to see as the output? So those things we can uh, mm, see here. So I just pressed this kilowatt plus JkVAR, so it will give the power flow in kilowatt and kVA. So we have to change it to mega MVA base, so that we can able to see megawatt and MVA megawatt values. Just a minute. Audible? Can anyone confirm whether I'm audible?
Yes, sir.
Yeah, okay, good, fine. uh, So here we have some reporting option. So that reporting option I will tell you. So here report manager. So this will be our report manager. So in the report manager we have the multiple option. Complete is the total in. It will give the overall the power flow load flow analysis result with considering the input and our output. That is the result. So if we need only the input alone, then we have to go to the input page, and we have so many things. So what are the inputs we need? Those things we can go. Suppose if we need only the result alone, so here are the results are there. Suppose if we need only the summary alone, that summary also we here we can execute. The result alone, if we need to see, then here we have to select the load flow report. Then viewing action, how we want to view. So viewer we can able to see in this desktop itself. PDF means it will generate the result in PDF. MS Word means it will generate the result in MS Word. Suppose if I am pressing for viewer, so it will show the result in one more tab. So it will come, and suppose if we need to some analysis means, so here the question symbol, uh, through that we can able to see some analysis that I will tell you how to do that. So after pressing this, here we can able to get the dialog box like this. Suppose if we want to see the bus voltages alone, so we have to select this bus voltage and what are the parameters if we want to see. If we click it means then it will appear here. Then branch result means what are the branches there, those branches will come here. So load detail means what all the loads are there, those details will come here. So but unfortunately it is not coming in this box because it is a trial version, I think. In the original purchased version, all the results by clicking, when we are clicking the value results, what are the things we need to do, so those things will appear. So from that, here one export option is there, no? So by clicking that export option, it will directly create a new Excel file. So in that Excel file we can able to do some analysis, but unfortunately in this demo version this is not available. Display option you need. Okay, then I will introduce another one load option, that is a lumped load. So we know the static load, no? So static load having, there is no rotating part. Okay, so lumped load is a load which has the combination of static load and dynamic load. I will tell you how to model. So in the lumped load, we have two options, single phase or three phase. So that we have to select, and as usual, name, then connected bus. In the nameplate, we have to model. How we have to model, I will tell you here. So here we have to model how much percentage is static load, how much percentage is lumped load. Sorry, dynamic load. So let's say the aggregated static and dynamic load is 5 MVA. So out of 5 MVA, 60 percentage I am considering as a constant KVA and 60 percentage is constant impedance. So constant KVA is our static load and constant impedance is our dynamic load. So by varying this slider, we can able to adjust the ratio, how much we can keep, 70/30 or 100. Suppose if we put everything in constant kVA, sorry, constant kVA is the dynamic load and constant Z is the static load. That you can able to see here. In the can able to see my cursor. So 100 percentage is the motor load and 0 percentage is the static load. Suppose if we want to consider 100 percentage is the static load, then we have to put it at this location. So the entire values will be 100 percentage static load. If we need to keep it to 50/50, then 50 percentage is the motor static load and 50 percentage is motor load, that is dynamic load. So up to this part, we have to model for this load flow, sorry, this lumped load. Okay, so for doing the load flow, so we can press this PQ. So it is automatically the load flow has been executed because I switched on this auto run on button. So it's executed the typical load flow study. So I will include this motor load also. So in the motor load, so we have to select the connection type as usual ID. In the nameplate rating, so how much is the power rating? So here by clicking this HP, kilowatt will come. By clicking kilowatt, it HP will come. So I'm just considering 1500 kilowatt. Okay, these other details it is taking from the library. If you want specific detail, these and all you can able to update it. Okay, so at this moment it is 1500 kilowatt. Okay, so now the load flow has been executed. So for if anyone is not clear with lumped load, I will once again explain you. Lumped load is a combination of static load this one and motor load this one. So the combination of both static and more dynamic load is modeled as a lumped load. So in that we can able to select how much percentage is the static load, how many percentage is the more dynamic load, that we can able to select it. When we can use it means in many industries, some of the loads are high power rating load, 100 kilowatt, 200 kilowatt, 500 kilowatt, 1000 kilowatt, 1500 kilowatt, 2000 kilowatt, like that. Some motors are higher in capacity, but some auxiliary motors are very small power rating in capacity, like 1 kilowatt, zero point 0.5 kilowatt, zero point 0.6 kilowatt. Some motors are 0.25 kilowatt, so like that, so their power rating is very very minimal. So if we model the entire auxiliary motor load, then it is a tedious task, so it is a time consuming task. In order to avoid that, so we what we will do, we will aggregate it. Aggregate means we are just grouping the entire auxiliary load as a single lumped load. That lumped load is this one. Okay, I hope everyone is clear with this lumped load. Okay, if you have any doubt as of now, you just turn on your mic and you can ask me. So I am, what I am feeling is that this session is not going as an interactive session. So if you have any questions as of now, you can just ask me. Okay, if there is no question, then we can move further. So now we will try to include the generator here. Generator. So generator, it's the single generator is for all the generator, whether it including diesel generator or the thermal generator or a hydro generator. So it's a single generator is available here. So in the generator, so first we have to update the ID. Then in generator, what we need to do, we need to select the operating mode, whether it is a swing mode or voltage control mode or megavar control mode or power factor control mode. So that operating mode, we have to select it. Okay, so at this moment we are operating at voltage control mode. So in this, I'm just keeping it voltage control mode. Then in the rating page, so we need to enter the power rating of the generator. So I'm just considering it is a 2 megawatt generator. Its power factor is 85 percentage. So in generator, the power factor 85 means it is a lagging power factor only. It's not a leading power factor. So the efficiency is 95. So up to this much, we have to include it for the generator. Okay, can you able to see, but unfortunately there is no power flow from the generator, because in the generator we have to include the operating value. So the ETAP software is not that much intelligence here to produce the power based on the load, unfortunately. So we have to, for the generator alone, how much at the particular load flow scenario, how much real power and reactive power the generator is delivering, that we have to enter it manually in these operating values, so that it will consider that value. Okay. So importantly, we have to see another parameter, that is alert. Uh, Alert, in unfortunately this demo alert is disabled. So alert, what it means, that if any values in this analysis, in this modeling is exceeding the typical value, it will show the alert. So that particular, by clicking that alert, we can able to see what all the parameters is exceeding the typical reference value, that we can able to see it. But unfortunately here we are not able to see that. Okay, so it's not delivering 2 megawatt, it's certified. Okay, so I will tell you what happened. So in the edit case, so we are just calculating the loading based on the design. So what it means is that for any load, this ETAP given some option, that is design, normal, shutdown, emergency, standby, summer, winter, etc. So what it means is that in a particular year, so presently, one loading patterns will be there. After 3 months, the pattern will change. Then after 3 months, the pattern will change. So in order to account that, so we can able to make some category in the software. So here they mention as design. So that design only we are considering in this edit case. That one only we are solving. So in the loading category, we are just considering the design, what are the load values particularly entered in the design, that design we are taking. And similarly in the generation also, we are just considering the values from the design. So we have to enter the value in the design also. So that particular value this generator will deliver. Okay, suppose if you want, if the generator is operating at a different power level, for an example, one time it will generate 2 megawatt, suppose in another time it will generate only zero point 0.5 0.5 megawatt, means for that condition, when we are going to do the analysis, that time we have to consider that one. So what I done, so in the edit case, in the loading, I just considered the design of the values entered in design for the load category. In the generation category, I just consider normal in place of design. So it means the reduced power generation capacity. So what value I entered in this normal, I just entered 0.5 megawatt, the generator has to deliver. So when the generator, when we are running the power flow, so the software, what it will do, it will consider the load from the design, but the value entered in the design, and for the generator it will consider what is the value entered in the normal. So that power value it will dispatch it here. So that is the only thing we have to keep it in mind when we are doing the generator modeling. So now again I am changing it to design category. So now it will deliver 2 megawatt. Now it is fine now. So for your for the example, so what I am trying to do in this modeling, so I'm just going to switch off this swing bus. So do you presume whether the load flow will run for this system? Yes, just to see with this voltage control it is running, but this generator we have to keep this as a swing generator. That is the correct one. So when the generator is operating in a swing mode, it will deliver. It can able to operate. So it can't operate in the voltage control mode. It has to operate in the swing mode only. Okay. Suppose I'm just connecting one more generator here. One more generator here at this 250 kV. Just I am putting swing generator. So this could be somewhere around 200 megawatt. So in the design page, it will not enable because I put it in swing mode. So design will not enable. So in the last session, we seen that three type of buses: swing bus, generator bus, and load bus. Since it is modeled as a swing bus, so it will deliver unlimited real and reactive power to the load. Okay, so just I'm switching off uh, this one. Just switching off this grid bus. So now also the load flow will get execute, but load flow will execute, but unfortunately this generator is not delivering any power because it is delivered by this generator. Suppose this generator is not in service, then entire power will be delivered by this swing bus only. Now if I switch off this generator also, whether it will run now, it will not run because there is no swing generator. So we will get the error like this: the system has no swing bus or generator, so our system will not run. So at least we should have one swing bus in the system. Okay, and what are the other components? Cable we have seen in that last session. Wind turbine generator. Okay, I will model one wind turbine generator through one cable. Have you anyone seen the wind turbine generator model? So in the wind turbine generator, what are the things we have to do? So first we have to understand about the wind turbine generator. So in the wind turbine generator, there are four types are there: type 1, 2, 3, 4. So type 1 and 2 is almost absolute in stage. So mostly presently we are using with type 3 and type 4 generators only. So that we have to select whether it is a type 3 or type 4 generator. So based on that, so that we have to select, and the operating mode we have to select. So once we change the type, then automatically it is changing its operating mode. So mostly type 4 generator will operate in voltage control mode only. So that option we just get enabled. So here some typical wind turbine generator library is there. Suppose if we want the generator to be modeled as per this, then we can model as per this library. So after entering this info page, we have to go to the rating page. In that one, the power rating of the generator is 2 megawatt. Then output voltage is 0.69 kV and power factor is 92 percentage. So these are the things we just model it from the library. Okay. So now whether the load flow will run for this case? Definitely no, because the bus voltage is 11 kV here, but the wind turbine generator voltage is 0.69 kV. Okay, so normally in a practical plant, so the wind turbine generator voltage will be in 0.69 kV only, 0.69 kV only, 0.69. So how we will connect? We will connect the wind turbine generator through a dedicated wind turbine generator transformer. So we will generally use one transformer here. So this transformer we will use. So the power rating is almost uh, higher than the wind turbine rating. So for time being, I just considering 3 MVA as the power rating. So the primary voltage is 11 kV and secondary voltage is 0.69 kV. Then impedance, I'm just selecting the typical impedance. The tap I'm not modeling any tap. So but in practical system, in most of the wind turbine generator transformer has this off circuit tap changer. The on circuit tap changer will not be available in the wind turbine generator. Mostly off circuit tap changers only available here. So in the grounding page, I'm just considering delta in the primary side and star in the secondary side. Okay, so now we have to connect the generator to this. So here some shapes are little weird, no? So for that, what we need to do, control R will rotate the connection. So if you need to rotate the equipment, then we need to press control R. Now suppose if we need to rotate this equipment, means we need to select and press control R, then the connection point will get rotate. Okay, now the wind turbine generator has been modeled. So for executing the load flow, we have to go to the load flow page. Okay, but we have not entered the cable model. Just a minute. So we have to enter the cable model, and the day I have told in the for the cable, we have to enter the cable ID. This is optional. Length. So length is mandatory. So just I'm keeping it in kilometer unit. Just considering 1 kilometer is the cable length. So in the library page, there are some standard details available. So from that, we can take it any one value, or we can enter as per our details from the cable manufacturer data sheet. Okay, so once we updated this library, then it will appear in this impedance page. This positive sequence and zero sequence impedance will be automatically updated once we model the cable in that library page. Now it will execute the load flow for this wind turbine generator. You can able to see this wind turbine generator is delivering 2 megawatt of just a minute. Can anyone confirm whether whether I'm audible? Hello, can anyone confirm whether I'm audible?
Yes, sir. Audible.
Yeah, okay, good, fine. So this wind turbine is delivering 2 megawatt of active power and 0 megawatt of reactive power. Okay, but can able to see in the transformer low voltage side, the real power is 2 megawatt and reactive power is 0. But in the high voltage side, can you able to see the real power is 1.99 megawatt and reactive power is minus 0.082 megawatt. So here the difference, why this difference is the losses in the transformer. So the power flow, the RO mark we have to see. So in the real power, it is flowing from this generator towards the system. So the RO mark is like that. So here it is 2 megawatt, here it is 1.99. So the transformer having the power loss. So after the power loss, we are getting the reduced value. So some amount of power is lost in the transformer. Okay, and here the reactive power is minus 0.082. So what it means is that the transformer, for the transformer operation we need some reactive power, no? So that reactive power, the transformer is taken from this source. So only it is generating minus, it is taking 82 kVAr of reactive power from the source. Suppose if we model this generator also delivering some reactive power, then this transformer will consume the reactive power from the generator, and after the remaining reactive power only we can able to see it in the bus. Impedance page perfect here. So Q max means how much we can able to deliver. So let's say I'm entering 0.1. Control mode. Point 0.1 can able to see. So this generator is delivering zero point 0.1 megawatt of reactive power. So can able to see this transformer high voltage side, it is not 0.1, it is 0.018. So the sign is positive. Last time it is negative, now it is positive. It means the both real power and reactive power is flowing from this generator towards the system. So earlier reactive power is consumed from the system by this transformer. Now the transformer is consuming the reactive power from the generator. So the remaining reactive power only is flowing into this system. Okay. So that's all for this wind turbine modeling. Some other modeling is there, that these are all the things we need it for the short circuit study, not for the load flow study. I will explain other things in the short circuit study. Then after that, so these are all the elements mostly we will use. Okay. Uh, and what are the other things we can do? So for the exporting report, just we have to complete press it, click export. So we will get the report like this. So it will generate the report and it will show. If in anyone's university, if you people having the option for this software, then better you can take the training, or you can use that software ETAP software available in the university, because in demo version some feature may not available, but unfortunately this report feature is not available in this demo version, so only it is not coming. But in a licensed version in the university, you can able to see those things. Okay. Mm. And some option is there, that is PV array. In the PV array is available in this AC component also. Similarly, in DC component also. DC component also, this will be the PV array. So if you are doing the AC load flow analysis, that time you have to use this one. Suppose if it is a DC load flow analysis, then you have to use this one. So in the AC load flow analysis, so we have to connect the PV. Then we have to model how many solar PV modules we have, how much, what is the rating of the inverter. Those information we have to add it. So in the solar panel, what is the rating of the solar panel? Single watt rating. For an example, it is 350 watt peak panel, means we have to enter is 350. Then like that, how many number of panel is there? So that we have to model it. So suppose if it is one panel, then it will also become 350. Then VMP means voltage at maximum peak power. VOC is open circuit voltage. Okay, IMP means peak current. ISC means short circuit current. Okay, so these values we need to enter here. The library is there, but unfortunately is disabled here. So from that also we can able to select those values. That if I'm just putting some random values here. Okay, so now we just modeled the rating of one PV panel, then array. So panel is a one element, array is a uh, uh, multiple panels. In panel, only one panel will be there at the wattage of 350 watt peak. In array, we have many number of panels. So 350 watt peak panel. How many number of series connection we have? How many number of parallel connection we have? So these things and all we have to calculate based on the particular site condition only. Just I am putting some 8 number of series connection is there, and 10 number of parallel connection is there. Okay, so the total power rating is 28 kilowatt. Let's say this also 10, then totally 35 kilowatt we have the capacity. Okay, so the total solar PV system capacity is 35 kilowatt. So then we have to model the inverter. So some values are it's taken from the PV array page. So we are having the total kilowatt as 35 kilowatt, and system voltage also it calculate. It is taken from this one 350 volt. Then it calculates the equivalent ampere here. Okay, so this part we have to model in the inverter part. So what is the rating of the DC part and AC part? So we have 35 kilowatt in the DC part, no, the same also we can consider 35. With this that one we can't directly edit it here. That part we have to edit in this inverter option. So this inverter modeling part alone we have to do it in this inverter editing option. So in this option, so we have to consider the DC power rating is 35 kilowatt and the DC voltage is 350. Okay, so the efficiency part is here, so that we have to enter it accurately. Then in the AC part, in the AC side, how much is the kVA rating and how much is the voltage rating, that part we have to update it here. So now it is modeled. So another one more option is there, that is PV array to the inverter. So in the DC side, after the solar PV panel, there will be a DC cable between the solar PV panel to the inverter. So if we are modeling that cable separately, then this one is not required. Suppose if you are not modeling separately, we have to model the DC cable. If we no need to consider that cable, then we can ignore it. If we need to model, then we have to model inside this cable library. So just I am taking some random value. So I'm just selected one 250 square cable size single core copper cable. Uh, it is connected between the solar PV array to this inverter. So that much only for the solar PV panel. Can you able to see this solar inverter is delivering almost 0.032 megawatt. So what it means, it is delivering almost 32 kilowatts, 31.5 kilowatt it is delivering. So some of the thing what we need to consider is that this PV curve and IV curve. So two things we need to know. One is the PV curve and IV curve. So the solar PV system, it's not like our typical thermal power plant or hydro power plant. So for the solar PV system, it's little different from our conventional power generation. So for before start modeling any solar PV system, you have to understand what is PV curve, IV curve, what is the irradiance. Those things we have to first understand, and after that only we have to model the solar PV system. So like that we have to model the solar PV system. Any doubt in this wind turbine modeling and solar PV modeling? Okay, good. If there is no doubt, then that's all from my end for today's session. So, yeah, in this session, we have just recall what are the things we have seen in this session. So, we have seen the generator component in this session. So, how to model the generator, and also we have seen the lumped load. So, the lumped load is the combination of static load and dynamic load. So in the lumped load, we have to select how much percentage we need static and how much percentage we need dynamic. So that one we have to consider, we have to select it. And also we have seen the wind turbine generator. So in the wind turbine generator, how we have to model uh, those things we have seen. So in the info page, so first we have to select what is the type of WTG, whether it is type 1 or type 2 or type 3 or type 4. So those things first we need to select it. Then after that, in the rating page, so we have to enter the power rating of the generator, then power factor, then efficiency. Okay, so these are the things we need to consider for the wind turbine generator. And then lastly, we seen the solar PV system. So in the solar PV system, so first we have to model this solar PV panel. So this is the individual model. So from that we have to we have to model the solar PV array. So how many number of panel is there in series and parallel for the particular inverter? Then we have to model the inverter. So in the inverter page, so we have to model the inverter through this inverter editor. So in this inverter editor, in the rating page, so we have to model the DC rating, kilowatt, voltage. Then this Vmax and Vmax is the DC bus maximum and minimum operating voltage. So 90 percentage is the minimum voltage and 110 percentage is the maximum voltage. So and also we have to consider the efficiency for the different loading. So suppose here it is 100 percentage, the efficiency is 90 percentage. So when the inverter is operating at 75 percentage loading, then it is efficiency is 90 percentage. So like that we have to model the efficiency. Then the AC power rating. So we have to consider the kVA rating of the inverter, then voltage, then full load current. If you enter any two parameter, then the next parameter will be automatically calculated. So these are the things we have seen, and also what we have seen this auto run on and off feature, and also the report manager and load flow analyzer. So these are the things we have seen in this session. So today is the last session for the load flow analysis. So I am suggesting everyone to just go through the components in the ETAP software before the next session, and I am suggesting you to start using this software for minimum 20 to 30 minutes touch base in a day, so that you will become familiarized with the usage of the component and usage of the software in a month's time. So that's all from my end. If you have any questions, you